I'd like to introduce Alessio Buccino, a lead dev of the SpikeInterface project. So we're switching gears here from optical physiology now into extracellular electrophysiology. So the last two talks were about taking optical imaging and processing that data and visualizing it. And this is kind of an analogous workflow for extracellular electrophysiology, where you have raw voltage data and you need to read that data into a pipeline, get spike sorting and visualize the results of that. The SpikeInterface platform has become really central to the NWB ecosystem. We work closely with Alessio because the platform really allows us to support convenient conversion from a large number of different proprietary formats, as well as convenient access to really state-of-the-art electrophysiology processing pipelines. So I'm really excited to hand the mic over to Alessio to show you all the great work that he's been doing with SpikeInterface and how it relates to NWB.
All right, thank you very much, Ben. And thanks again to you and to Ryan and all the others for the invitation to present SpikeInterface. It's actually a very nice opportunity for us to show these tools to the community. And so whoever wants to actually follow actively this tutorial, this is going to be hands-on. So you can actually go to the chat and go to this Spike Tutorials GitHub repo, which is going to look like this. And then you can just go ahead and clone, probably using a HTTPS, clone the repo. And you can do it from your terminal. And then you would just clone the repo. So git clone. 1 sec. Oops. Okay. Yep, there we go. Can you see well? Is it large enough?
You can see it. It's a little small.
Okay, I can make it bigger. Okay, that's better.
That's good.
So you can just clone it. I already cloned it, and then would basically clone this Spike Tutorials repo. And you will see that in this repo, you have 3 main tutorials. So we're going to go into this NWB developer breakout session, September 2020. There we go. And then we have a bunch of files. But let's see on GitHub how it looks. And also because in the README, we have instructions on how to get everything installed. So inside this basically NWB tutorial folder, you're going to find an environment.yaml like Carson shown before. We can just create a new conda environment, but you can copy paste this command. So conda env create -f environment.yaml. And this will basically install all the required packages that you need for the tutorial and create it in an environment called Spike Tutorial, which I've already created. So after you're done, you can just activate the environment on the activate Spike Tutorial, right? And then we just need to install an extra package, which is phi, and we need to install it with these like 2 commands as well. So just go ahead and copy these after you've activated your environment and just run enter, and this will get phi installed already, right? I've done this already. So then after you've done all the installation, maybe it's going to take 1 or 2 minutes, you can just launch a new Jupyter notebook. Right, and this will open your favorite browser, Chrome, and it will show something like this. All right, then we need to do something else before running the tutorial, and this is getting some data. So we have uploaded some data to Zenodo, and you can go to this link. Yes, here we go. And basically, I would like you to download this OpenIFIS dataset on your computer. It's, yeah, less than 1 gigabyte, so it might take a couple of minutes. But after you've done that, you can just basically drag it into this NWB folder, and you can unzip it there. And so this is going to create a folder called OpenIFIS dataset. And this basically contains real recording acquired from this OpenIFIS acquisition system. And the recording is from Hippocampus CA1 region, and it was recorded from the Center of Integrated Neuroplasticity in Oslo. And once you're done, you can just launch your Jupyter notebook and open this SpikeInterface tutorial, right? So I don't know, can I have a show of hands how many are actually actively like following hands-on and downloading and installing everything? You can also just use the raise or raise button in the chat. But is anyone actually following, trying to do this live? Otherwise, I just go ahead and show what I have. Okay. So are you actually, were you able to, B2, right? Were you able to download everything, and is everything done already? Can I start, or do you need another couple of minutes? Still downloading the data set. Okay, so maybe I'll start just by, while the download is going, I'll just briefly introduce SpikeInterface and what we're going to do in this tutorial. So SpikeInterface is actually a Python meta package which wraps 5 other sub packages, and each of these package is designed to do something slightly different in the Spike sorting or electrophysiological analysis pipeline. So we have Spike extractors, which basically takes care of the input output and also loading probe information into your recordings. Then we have the actually Spike Toolkit should be first. Spike Toolkit contains all the tools that you need to pre-process your data, do some post-processing of your data, and also it has tools for validation and computing quality metrics on the Spike sorted data, and also for automatic curation. And we have the Spike sorters package, which is it contains wrappers to many of the most popular Spike sorters. At the moment, we support 10 different Spike sorting tools. And then we have Spike comparison, which is instead a package that allows you to compare the output of different Spike sorters with and without ground truth. And then Spike widgets, instead, it's a package that allows you to visualize what you're doing, and you'll see later throughout the entire pipeline. So we first start by loading some data into Python using Spike extractors, and then we'll add some probe file and probe information. Then I'll show you how to pre-process the signals before Spike sorting. And we run a couple of popular Spike sorting algorithms that are kind of Python compatible. Actually, one of them is MATLAB based, but I'll show you how to run it as well if you have MATLAB installed. And then I'll show you 3 methods to curate the Spike sorting output. One is the manual curation using 5. Then we'll have an automatic method using some quality metrics computed with the SpikeInterface. And then we have this consensus-based or ensemble Spike sorting, in which we are going to combine the output of multiple sorters to automatically curate the data. And finally, we're going to save the results to NWB. All right. So is the download done? Almost, but okay, I'll start. Otherwise, I'll run out of time. Okay, but then you can catch up later. So first of all, we need to import these different modules of SpikeInterface, and we'll import them like this. And then we'll also import matplotlib and NumPy, just because it's nice to have them there. Okay, these are all imported. And then we need to start loading our recording. So since this is an OpenIFIS dataset, we're going to call upon this OpenIFIS recording extractor and just pass the folder that is just comes out of the OpenIFIS acquisition system. Okay, so it loaded OpenIFIS data, and we're going to see later that this is actually interchangeable with any kind of extractor that you might want to use. Actually, I wanted to mention, if you have some data that you would like to try, these are the list of all the extractors that we actually support, all the recording extractor. So if you have data in a certain format, like in intan, or if you have binary data or multi-channel system that you want to try, we also have like Spike GLX and all the NeuroPixels related formats you can try. I recommend if you have like a small data set, it's fine, but if you have like an hour-long data set that we won't have time to run Spike sorting on that, so In this case, I'm just gonna use a short data set just for showing the different tools. And also, some extractors come with some specific requirements. So in order to run some of these extractors, you need to install some extra packages. So basically, by running the extractor, if the package that you want to, that it needs, it's not installed, it's gonna say, look, I need these 2 or 3 packages in order to run. So you can just pip install them and it should pop up in this list. Okay, but after we have loaded our data, we have this recording variable, and this is an object. And it's an object of a type recording extractor. And basically, the idea of this object is that it's an interface to the actual file. So we're not actually loading the data into memory, but we just have a set of methods from this object that allow us to retrieve all the information that we need in order to basically build and build our processing pipeline and spike sort our data. So it will allow us to access information about the channel IDs, channel locations, if they're present in the file format, the sampling frequency, and of course, we can retrieve the extracellular traces. So just to show how this works, we can, for example, access the channel IDs by calling the get channel IDs, sampling frequency with get sampling frequency, and the number of channels we get num channels. And we can plot all this information. So in this case, we have 32 channels from 0 to 31. Sampling frequency is 30 kilohertz. And again, number of channels, 32. We can also extract traces, and this is done in a lazy fashion. So when we want to extract some traces, we can pass a start frame and an end frame. And basically what this function will do, it will just load into memory. And sometimes when possible, we don't even load into memory, but we just memory map the file to save some RAM. But basically we can call this get traces and also pass this argument to just retrieve the time interval that we want. In this case, we'll just retrieve 2 seconds of the data. So from 0 times the sampling frequency to 2. And this will return a NumPy array with number of channel times t, where t is the number of samples. And as expected, since the sampling frequency is 30 kilohertz, we have 32 times 60,000, right? So this could be useful if you wanted to basically retrieve some snippets and plot them, but the Spike widgets package, as I mentioned before, allows you to basically have some convenient function to show how the recordings look like. So we can have this Spike widgets.plot time series and just pass a recording extractor. And this will actually show a short snippet of the data, in this case, like 300 milliseconds. But we can easily also increase or pass any time range that we want. Let's say we want to, the range, we want to plot from 1 second to 3 seconds. There you go, right? And we can just check it out and see, there seems to be some spiking activity. Okay, this is good. On the other end, it seems that this would be channel 2, 0, 1, 2. It might be broken. See, it has some nasty oscillations, and maybe this channel as well. But we'll see later how to deal with that. We can also plot other things. We can plot, for example, the spectrum of different channels. And this will internally compute the spectrum and just plot it whenever it is ready. So we can see that channel 0 and 1 is this orange and blue. They look quite fine. And this green one, channel 2, has some very high low frequency components. So we're going to remove this channel later before the analysis. The next thing you might want to do is loading some information about how you recorded your signals. So these 32 channels actually are the output of 8 separate tetrads that are mounted on 2 different drives on the 2 hemispheres of a rat. And so basically we know that these channels, they go together in like 4 by 4. So we have to, we can tell SpikeInterface that these channels actually are not separate files, but some of them make up some groups. And in order to pass this information, we can do 2 different things. We can either use the set channel groups method of the recording extractor, and then you would just pass a list of the ID of the group that you want to use for each channel, or we can load a prop file. And the prop file is .prb files that I believe was introduced from the Cluster and the Phi team now probably 5 years ago or something. And now it's also being used by other Spike sorters like SpikeInterface and so on. So we thought about supporting this kind of format in order to pass this probe information. And this is how a probe file looks like. So it's basically a Python dictionary in the syntax. And each key is a channel group. And we can see that in this case, I created this probe file. So we have from 0 to 7, so 8 channel groups corresponding to the different tetrads. And then for each of these key in the values, we have another dictionary in which we have to basically write down which channels this channel group 0 is going to have. And we can also optionally pass the geometry of the channels. Of course, this is not real geometry. So this would mean that this usually assumed to be micrometers. So of course, this is too close to be like a single tetrad. But this is just for visualization. Visualization is going to help us out a lot when later we're going to export the data and manually curate it. So in order to load the probe file, we can just do recording.load probe file and pass the probe file, in this case called tetrad32.prb. And very importantly, this does not load the probe file in place, but it returns a new object that I'm going to call recording.prb. So after we have loaded the probe file, we can actually see what were the original channels, and it's same from 0 to 31. After we have loaded the probe file, we still have the same channels, but now we actually also have channel groups, and we can retrieve them by these get channel groups. And we can see that the first 4 channels are group 0, the second 4 are group 1, and so on. So it did what we wanted it to do, right? And then we can also see that we have loaded location information, and we can use this widget called the plot electrode geometry. And this will plot basically the locations that we set for the different electrodes. And you can see that between channel 3 and 4, I increased the spacing because I know that these are basically, these tetrads belong to different drives in the different hemispheres. Okay. And so now we have seen this group and location, and we call these to be properties, not properties. And the group and location are actually built in the SpikeInterface framework because they are very important for Spike sorting. So many Spike sorters use the location information, and they also can use the group information in order to basically split the recording in different groups before Spike sorting. But in general, we can actually add any property that we want to any channel for the recording extractor. Similarly, for the sorting extractor, in which we'll see later, instead of channels, we have units, and each unit is basically a cluster or a putative neuron found by the Spike sorter. Each unit can have either properties, and properties basically are things that belong to a unit in general, but we also can have Spike features, and features are basically things that belong to single spikes in a unit. And an example of a feature are waveforms or spike amplitudes. While, for example, an example of a property of a unit could be the maximum channel where it was found, or the average waveform, right? They don't belong to single spikes. We can actually check which properties are available in the extractor for all channels using these get shared channel property names. And we can see that initially in the recording that we loaded from the OpenIFIS directly, we already have the group information, but actually this is initialized to be all zeros, so it doesn't tell us anything. But after we have loaded the probe file, now we have group and location. And as we've seen before, now the group actually has some meaning. It shows us, it tells us which tetrad the channel belongs to. And we can also add new properties. For example, as I told you before, in this case, we know that the first 16 channels belong to the left hemisphere, and the second 16 channels are from the right hemisphere. And so we can basically set these properties by using the set channel property function of the recording extractor. And we have to pass basically the channel ID, the property name, and the value. So in this case, I'm just looping through the channels. If the channel is less than 16, then we'll set it to left. If the channel is above 16, then we'll set the property name hemisphere to right. So after we've run this and we check again the shared channel property names, we can see that hemisphere pops up here. Okay, so this is basically a brief introduction on the Spike extractors part. So how to load data and load probe information into your recording extractor. And now we'll move on to the Spike Toolkit module. And this is very useful for doing some pre-processing of the recordings. And some of you may argue that some Spike sorters already have some pre-processing available, for example, some filtering, some CMR. But the idea of having pre-processing before Spike sorting is also that we can standardize not only the Spike sorting, but also all what comes before and what comes after Spike sorting with some widely tested and continuously integrated functions. So in this case, we'll start by applying a bandpass filter to our recording, and this is done using Spike Toolkit from the pre-processing submodule of Spike Toolkit just by calling this bandpass filter. And we're going to filter between 300 Hertz and 6,000 Hertz, which is normally what it's used for getting the frequency of the Spike sorting of the Spike signals. And this returns yet another recording extractor. And the nice thing about this, since this recording_f is another recording extractor, is that we can use exactly the same functions that we have done before, that we have used before. So we can forget exactly, so actually let me print the type of this recording F. So you can see this is a bandpass filter recording extractor. But if we ask whether this is an instance of the basic recording extractor, is instance. Yes, we see that this is true. So basically also on this recording_f, we're going to have all the methods that we've seen before: get channel IDs, get traces, and so on, right? And this makes it very easy to build the processing pipelines. So on top of the filter, we can add some other processing pipelines. But before doing that, just by looking at the signals, we notice that basically the first 16 channels, which are this one on the top, are way more active than the second 16 channels. So for the rest of this tutorial, I'm just going to throw away these second 16 channels, and we're going to focus on the first 16. And we can do this quite easily using what it's called a sub-recording extractor. So we can basically return a new recording extractor that comes from this recording_f, but it only uses channels from 0 to 16. And we can see now that this new recording extractor has channels from 0 to 15. It keeps the grouping information. Now we have thrown away tetrode 4, 5, 6, and 7. And also if we plot the time series, now we only see these first 16 channels, which seems to be quite active. But as we've seen before, and we can see it here as well, channel 2 seems to be a bit noisy. So we might want to throw it away before running our Spike sorting. And the way we can do it is using another preprocessor, which is these remove bad channels. So we can just pass our sub recording that I called here recording 1. And then we want to remove this bad channel ID number 2. So after we run this, we can see that channel 2 was actually removed from the channel just by calling these get channel IDs, and also from the groups. Now we only have 3 zeros, while before we had 4, right? Okay, now let's go on and let's apply another very common pre-processing step, which is a common median reference. And we're going to pass in here this recording without channel 2, which I call recording removed noise. and we're going to set the reference to median. And this will basically, at each time step, remove the median of all channels. And this is very important to remove what we call common noise, which might be coming from line noise or from a movement. But it's basically, it should remove all the, it should clean up our recordings. And we can see now how the time series look. So check out the difference. So all these kind of shared oscillations and activity that you can see are very much decreased. And this highlights even more the nice spikes that we can see here. Okay. And again, it keeps all the information of the recording. Okay, now, so this recording is actually around 10 minutes, which is going to be a bit too long to spike sort. So again, we can use the sub-recording extractor not only to subselect a set of channels, but also to basically cut our recording basically in time. In this case, I'm just going to cut out 2 minutes from 200 seconds to 320 seconds. And so from now on, we're going to use these recording subs. So 2 minutes, 15 channels, right? Because we removed one. And let's move on to caching. All right. So as I mentioned before, all these operations in SpikeInterface are lazy. So you might have noticed that when we filtered our recordings, it didn't take any time. And of course, if you're used to any like processing of extracellular traces, you know that actually filtering take time. So what's going on? Lazy means that actually the operation that you, we can build these pipelines, but these operations are not actually performed until you call the get traces methods. So only when we call the get traces method, for example, in this case, the data was filtered and CMR was applied, but only on like 300 milliseconds. So this is very nice if we just want to skim through the data and check out the recordings and so on, because it's very light in memory and fast. But you can imagine that if we want to do some something which is a bit more intensive, for example, if we want to extract each waveforms after spike sorting, this is not a right approach, because in that case, each waveform would be like filtered separately, a CMR would be applied separately, so it won't be performant at all. So in order to avoid this, after we are done with our pre-processing pipeline, I usually recommend to cache the recording extractor. And what caching does is basically retrieving all the traces, and it will do it in chunks. So even if you have a very long recordings with a very high number of channels, it will try to do it without consuming too much RAM, and it saves it on a binary file on your file system. And the cache recording is another recording extractor, so it has all the same methods that by now you should be familiar with: get channel IDs, get channel groups, and so on. But under the hood, actually, this recording is actually, it points to a .dat file, so a blob of binary data, which is saved in your temporary folder, right? But this might be not the best position to save your data, because basically if you reboot your system, this temporary folder will be gone. But by default, any recording actually has its own temporary folder, and this is used, as we're gonna see also later, it's used to dump different kind of things like waveforms and so on that might be very heavy on memory, but instead what our proposed approach is to basically save these temporary files and then memory map them, so we can very quickly access the files without consuming too much RAM. But if we want, for example, to move this file to something that we want to use even later, we can just use the move to function, and this will basically move this file into the current folder, call it filtered data.dat, and now the file name is updated. Okay, now we have a nice .dat file, and as I said before, if we reboot our system, our .dat file will still be there, filter data.dat. However, the .dat file has no information about the shape of the recording, so if we have this .dat file, it would be of no help if we can basically also know how many channels are there in the recordings, how many frames, and so on. So in order to basically keep this information, we have a dumping system. So any extractor, it can be a recording extractor or a sorting extractor, can actually be represented as a dictionary. And this dictionary basically holds every information that you need in order to reinstantiate the same object from a file. So it will tell us which class it is, and you can see here is a binary dot recording because we cached it. It tells you which module it comes from, which keyword arguments were used to instantiate this object, and also all this metadata, all these other key arguments that will be used to reinstantiate the object just from this dictionary. And also it keeps information about the grouping properties and the location, and we know the version and whether it can be dumped to a file or not. And this is very important for provenance. So basically, whenever also we'll see later when we spike sort our data, dictionary will be saved along with the parameters of the spike sorter so that it could be fully reproducible. Just by from this dictionary and the spike sorting parameters, we could rerun exactly the same spike sorting. Now, this is a dictionary, but we want to dump it to a file. So we can either dump it to a JSON file or a pickle file. The pickle file is convenient because it allows you also to store properties, and for sorting extractors also features. So if we dump to JSON, instead only group and location information are saved. But we can just dump it to a pickle file using the dump to pickle function. There we go. And then let's say tomorrow you want to start back your analysis, you're going to go on with spike sorting. You can load back your recording from the pickle file, just using the load extractor from pickle and passing the recording.pickle. And this basically returns exactly the same object that we saved, which was the recording sub, or actually the recording cache. Yeah, but basically we can see it's exactly the same object. And it also, let me show that as well. Yes, it also keeps all the information loaded, .get shared. So it also keeps the information about the extra properties that we added. In this case, we added the hemisphere property, and it's still there. So this is a good way to actually, also if you do some computation, to dump everything you have and load it back. Okay, now let's come to the fun part. Let's do some spike sorting. So spike sorting is handled by the spike sorters submodule of SpikeInterface. And first of all, we can check which spike sorters we have installed on our machine. You can see in this case, not many, because in the environment file, I only had the cluster package installed. But this is going to be enough for this tutorial. And actually, we're going to try to install another spike sorter on the fly later. But spike sorters comes with some very convenient functions in order to retrieve the parameters that come with the different spike sorters. So for example, in this case for cluster, we have the adjacency radius, thresholds, the text signs tell you whether, asks you where spikes are negative or positive, and so on. And you can switch these to any other spike sort. Kilo sort. Spike sorter that you'd like. And these are basically all the parameters that are exposed through SpikeInterface, which might not be all, but we try to basically cover most of the parameters that an average user or also an advanced user might want to change. And also we have a get params description function, which basically it returns a dictionary, and it aims at basically briefly explaining what different parameters do. Right. In this case, the adjacency radius is the radius in micrometer to build channel neighborhoods. Right. And then we have the main function of this spike sorters package is this run sorter. We can see the signature of this function. So it requires a sorter name or a class, which can be, for example, cluster. It needs a recording extractor, an output folder optionally. Otherwise, another one it's created with the name of the sorter. Whether you want to delete the folder, and if you want to spike sort your data based on some grouping property, as we'll see later, we're going to use this to spike sort divided by group, and other functions if you want to use multiple jobs and so on. And also there are other convenient functions that further wrap this run sorter function, but for different sorters. So we have the run cluster function, which basically runs cluster. So it calls the run sorter. And also you can pass all the keyword arguments, so all the parameters that are Spike sorting specific. And like cluster, we have like run mountain sort for, right? And it's the same signatures, but in the different Spike sorter, you're gonna pass different parameters. Okay, so how to run Spike sorting? It's very simple, one line of code. So we have Spike sorters, run cluster. We pass our recording extractor. We say which output folder we want to use. If we want, we can pass some cluster-specific parameters like the adjacency radius, and we can make it either verbose or not verbose. So very importantly, these will not use grouping information because we're not telling the Spike sorter to do so. So I'm not going to run this because I'm going to show you how to run Spike sorting divided by group and how this is basically performed under the hood. So in order to Spike sort by group, we need to pass this grouping property equal group argument. And what internally this is going to do, it's going to split our initial recording depending on the group. So in this case, we have 4 groups, right? And this is exactly this recording. So from the first group, we actually removed 1 channel, as you can see here. And then it's going to run Spike sorting separately for the different groups. And then it's going to output a multi-sorting extractor which put together the output of all the different Spike sorters, but internally you can actually still access these different Spike sorters for each group. So now I'm actually running this Spike sorting with cluster, and if we check on our terminal where we run the Jupyter notebook from, it tells us that basically it's running different shell scripts, right? It's running this run cluster, 1, 2, 3, 4. So what I want to show you is how internally this is done. So let me open Atom. Okay. Too much stuff is open. Let's close some. Okay. So you can see that it created this folder that we used, and inside there are 4 different folders, 1 for each group. And then internally, in each of these groups, we have this run cluster bash file. If you use Windows, this is going to be a bat file, and this basically tells which command it's been running. So it runs cluster on this config param file with this override. The config param file is where actually all the parameters from cluster are stored, and then basically for each of these we also have these SpikeInterface params or Json, and this is basically what I mentioned before. So this stores the parameters of the Spike sorter and also the recording which is on which the Spike sorting is run. In this case, it's a sub-recording extractor. And one of the keyword arguments is the parent recording, so the full recording. But below, we're going to see that only the first 3 channels are basically kept in this recording extractor. Okay, now let's see how this is doing. It's going to take maybe a couple of minutes. Actually, any questions so far? No, that's good. Means everything is super clear. Okay, let's give it another 30 seconds. There we go. Cluster found 52 units. And if we print the type of this sorting KL, we can see, as I said before, this is a multi-sorting extractor. And this object actually contains a list of the different sorter that are basically merged into this object. And you can see that each of these sorter is a cluster sorting extractor because it accesses the output of the cluster Spike sorting algorithm. Okay, so we can actually, but I'll show you later, but we could see here that the sorting extractor object also has some convenient functions to access different information about the recording. So you can use sorting cluster.get unit IDs. And this will print the list of units that you have, and then we could have like a get unit spike trains of unit 0, and this prints basically the frame number or the sample number in which there is a spike. So not the time. In order to get the time, you will need to divide by the get sampling frequency. Right, and this time in seconds. Okay, now we're gonna install on the fly another spike sorter. This is a MATLAB-based sorter called Ironclad, developed by the James John at the Flatiron Institute. And I just want to show you how to actually install this new spike sorter in SpikeInterface. So first of all, we just need to clone the Ironclad repo. I'll just clone it in the same folder. Okay. Almost done. Yeah. All right, done. And now we just have to, so each spike sorter comes with a class that basically wraps the setting up of all the parameters and converting the file formats and the running. In this case, for Ironclad, it's called Ironclad sorter, and it has a function which is called set Ironclad path. So this will tell SpikeInterface that Ironclad is installed in this path. And in order to do that, we're gonna basically internally an environment variable called Ironclad path. It's actually set in your system. So you can see that in this case, it points to the Ironclad that I just downloaded and pointed to SpikeInterface. And now if we run install sorters, we can see that alongside with cluster, we also have Ironclad. Great. So now let's run the same. Let's run Ironclad, and let's see. Let's also run it by group and make it verbose, and let's run it. So in this case, since I'm not running it, yes, question? No? Okay. So now it's running the shell script, and you can see that internally, we call a MATLAB script from Python. So MATLAB is instantiated, and then Ironclad is actually run, and then it's going to be doing that for the 4 different tetrads separately. But Ironclad is relatively fast, so this will take basically maybe 50 seconds to spec sort the full thing, right? Let's see. The first one is finished. Actually, the second one is finished. So the other ones are running. Let's give it another 30 seconds. Yeah, but I can assure that Ironclad is actually one of the fastest spec sorted. Also, I would say with kilosort 2 is very fast. And if you have probes with a high channel count, you should give Ironclad a try, because that was developed also mainly for NeuroPixels data, similarly to kilosort 2. And it also has drift correction, and it has quite good performance as well. Okay, let's see, last one going. How am I doing on time? Okay, 15 minutes, not too bad. All right, last one. Of course, you can run it in parallel as well. But if we run it in parallel, as I've shown you with cluster before, since basically new processes under the hood are spawned, you wouldn't be able to see the output in the Jupyter notebook, but you could only see the output in the terminal from which you open the output. Okay, so it's finished, and Ironclad found 13 units. So cluster found again 51, so way more, actually 52. And we're gonna try to figure out whether these 13 units are good, and if cluster found too many, and in the manual curation part. But as I said before, we have these convenient functions, get unit IDs and get unit spike trains, to access the information that we need from this sorting extractor object. And also we can use some spike widgets to plot, for example, the rasters, or we could plot the autocorrelograms, close correlograms. You can actually browse what's available just by using the tab plot. All these plots are available. Like, right. Okay, so you could also, after you've done spike sorting, if you have the output of your spike sorter, then you could also reinstantiate a sorting extractor object just by using the proper extractor. But unfortunately, this cannot be done if you spike sort by group. But as I showed you before, basically, internally, when we spike sort by group, different folders are created for each group. So in this case, we can just call the cluster sorting extractor on this result split cluster 0 folder, and this will return the unit IDs from group 0. And you could do that actually for all the others. Okay, after we have spike sorted our data, we can do some post-processing. And post-processing means basically combining the recording and the sorting to extract the relevant information, such as waveforms, templates, maximum channels, PCA scores, and so on. And we can also classify, like we can also extract some waveform features that could be very important for example, classifying neurons as excitatory or inhibitory. And this is a quite recent addition to the package. So in order to extract waveforms, we can just call getUnit waveforms and pass a recording and a sorting object. And we can see that this is going to loop through. I'm using the Ironclast one, otherwise the class has too many units for this tutorial. And then we can, this returns a list of NumPy arrays, so we can just check the shape of this waveform from the first unit or from the second unit. And you can see that both of them, this like number of spikes, number of channel, and number of samples. But you might have noticed that they both have 300 spikes, which is, it might, you might raise an hour. Is it possible that they only have, they both have 300 spikes? Actually, let's check. So let's check how many spikes are in the spike trains for unit 0. It's way more. It's 1,562. So by default, when extracting waveforms, only a subset of waveform, basically 300, are actually extracted. And we can see that by checking the shared unit spike features, which is similar to the shared channel property that we used before. So in this case, we can see that alongside with waveforms, we also have waveform indexes. And if we actually plot these waveform indexes, basically we keep the information about which index inside the spike train has been used to basically retrieve the waveform, right? We can also increase this number by setting the max spikes per unit to like 500, for example, or if we want all spikes also to none or to infinite will work. Okay, but let's move on. So once the waveforms are basically computed, if we call again the getUnit waveforms, you can see that nothing is printed, and this is very fast. And this is because, as I said before, waveforms are cached and they're saved in the temporary folder that I showed before for the recording extractor. So there's a similar folder for the sorting extractor. In this case, is this bar folders, something unpronounceable. But if we actually loop through this folder, we see that we have all these raw binary files for each of the waveforms, right? And this makes it very memory efficient because all of these binary files are memory mapped, so they're also fast to access. But if we want to actually recompute the waveforms, we can use this recompute info equal true. And what we might want to do is to compute the waveforms split by group. So instead of using all the 15 channels, if we run this, we can see that waveforms are actually recomputed. And now I set this to none. So we'll see that all the spike trains will be used, and these are a bit slower than before because all the spikes are being retrieved. But this is almost done. Okay. And now basically we have a new property, not a waveform. So property belongs to a unit, which tells us on which channel IDs basically each unit was computed. In fact, if we look at the shape of these waveforms that we call waveforms group, we can see that some of them, all of them use all the spikes, but some of them have 3 channels, and these are probably the ones from the channel group 0, because we certainly actually these ones, because we removed one of the channels, and the other have 4. And we can again use spike widgets to inspect the output. We can plot unit templates, and we can just check how the output looks, right? And we can also, for example, plot autocorrelograms or cross-correlograms. We have, again, several widgets. Okay. I'm going to try to speed up a bit because we still have a few things to see. As I said before, we can compute extracellular features, and that's done with these compute unit template features. And if we want to see which features are available, currently it's this one: peak to valley, alpha width, peak to trough ratio, repolarization slope, and recovery slope. And we can just compute all of them by passing a recording extractor or sorting extractor. We can return a pandas data frame instead of a dictionary, and we can also upsample the templates in order to get better precision in this computation. Okay, so now it's computed, and we can see that for all of the units that we have, all of these extracellular features are computed, and we can further then use this information to move on in our analysis. And I refer here to some documentation about these features from the Allen Institute of Brain Science, where actually we collaborated to actually get this done. And yeah, there's a description of the different features, only these 1D features for now. Let's move on to validation. So we can also use SpikeInterface to compute some quality metrics. And so to say, basically to label units depending on some quality metrics, and also to automatically curate the output based on these quality metrics. And these are the quality metrics that are available at the moment. You can see some of them are really simple: number of spikes, firing rate, and so on. Some of them are more complicated. They require PCA scores to be computed, like isolation distance, silhouette scores, D prime. Some of them also measure drift, and we have signal to noise ratio. And this is a very important one. ISI violation tells you how much a unit is clean in terms of the refractory period, or how much actually it contains spikes that violate the refractory period. And we can compute any of these metrics with a specific function. For example, in the validation submodule of Spike Toolkit, for example, we can use this compute ISI violations, pass our sorting extractor and the duration in frames of the full recording that we got from the recording. And we can also compute the SNR. In this case, we also, of course, need to pass a recording extractor. And then we just plot it, so we can see different values, more or less SNR. But we can also use these compute quality metrics and pass these argument metric names, and we can pass a list of names and again return as data frame, which might be easier to handle if you want to filter out some of the units and so on. Again, also this part is inspired, and also it's a collaboration with the Allen Institute, and I just link here some extra documentation on what quality metrics mean and how is the distribution between different brain regions. Okay, we're close to the second last part, and this is going to be relatively quick. So I just want to show you how to curate your output with 3 different methods. So the first one is using Phi, which is a software for manual curation. And you can actually export any pair of recording and sorting extractor to Phi just by calling this export to Phi function in the post-processing module of Spike Toolkit. We need to pass an output folder. In this case, we call it Phi ironclast IC. We can split by a group if we have a grouping information, and we're going to recompute everything. So let's do this. So first it's recomputing waveforms, and then it's going to compute PCA scores. And then we'll be able to start Phi. Ben, is it okay if I go like 5 minutes over since it's the last one?
Yeah, I mean, you're the last one, so
yeah,
that's fine.
All right. Okay, almost done. And then we're gonna call the phi template GUI, but actually I wanted to show you because, yes. Also in my case, like similarly to Carson, it's running slower than before, probably due to Zoom. So I can blame Zoom for me being a bit late or, yeah, talking too long. Okay, so now it's basically fitting a PCA with 3 dimensions on a subset of waveforms and projecting all the waveforms on this PCA, and it's saved. And also it tells us you can run the template GUI now. You can run phi just by calling this, and that's what we have here. So we have phi. By the way, if you have exclamation mark in a notebook, it means you're running things on the terminal. So you can just call phi template GUI and point to the params phi in this phi iron class folder. And this is how phi looks. If it loads, there we go. So basically, very briefly, because we don't have too much time and there's a lot of documentation, these are all the clusters that we have. And so we can select one cluster. It's going to show you the average template, and we can also show many different waveforms, the amplitude over time, the autocorrelogram, and if you select more than one unit, it also shows the cross-correlogram. These are the PCA scores of different channels, and this is the trace view, and this is basically a representation of your probe, and that's how it is handy now to have basically split the different tetrads so we can see exactly where our units are. But then in order to manually curate the spikes, I'm going to just remove all the clusters which don't have this basically nice V shape in the autocorrelogram, and it means that probably they are kind of corrupted units or picking up noise. So to remove units or to label them as noise, in phi you can just press Alt-N. So this I'm going to remove, this one I'm going to remove, this remove, remove, and this one as well. I'm going to, let's see, yes, let's remove this one as well. Okay, the rest of them look fine. Also by looking at, this one is a bit borderline, but we'll keep it. The rest of them look fine. Okay, so after we're done, we can save with Control S or Command S on Mac, and we can just close. Okay, so we're done with this, and we can load back to SpikeInterface our curated data using the phi sorting extractor and passing the phi folder. And we can also ask to remove the cluster group that we labeled as noise. So if we do that, now we only have 8 units because we removed 5, and these are the unit IDs after manual curation. Okay, we could do the same for cluster, but it will take too long now. Okay, next, so this was the first way of curating, manual curation. Now let's try to do it automatically. We could do it automatically by basically thresholding some quality metrics. And in this case, I'm gonna just retain the units with an SNR greater than 5 and with an ISI violation threshold below 0.5. In order to do that, we can use this curation submodule of Spike Toolkit. And this works in this way. So we just have to say which, oh, this is IC. Oh, no. So in this case, I'm curating actually the cluster output to see how many units we get. So we pass a sorting extractor, this threshold that we want to use, and then we want to say, I want to remove all the units which are greater than this threshold. And then in this specific case, as we used before, we need also to pass the duration in frame of the recording. Oh, our audio is echoing too much. Let me try to. Is it still echoing?
Sounds okay to me.
All right, go on. So we run this, and then after we've basically this automatic curation from the 52 units that the cluster spit out, we're left with 10. So it's already a good cut. And then we can further a threshold, same idea on the SNR. In this case, we pass a sorting extractor, a recording extractor, the SNR threshold, and we want to remove all the units with the SNR less than 5. Okay, we still have 10. So this was actually, it allowed us to go from 52 units to 10 units. So basically 42 units are probably noise or not good units. And this is close to what we found after manual curation, 8, right? Okay, a third method is kind of experimental. And if you want to read more, we have a preprint out there for SpikeInterface in which we investigate these more for NeurPixels data. And the idea is to basically combine multiple spike sorting output and only to keep the units which are in agreement between multiple spike sorters. And of course, if you use more than 2 spike sorters, you're going to be more basically confident that the units that are found by, say, 3, 4, or 5 spike sorters are actually good units. Okay. And so in order to do that, we can use this spike comparison module, SC, and we can run this compare multiple sorters by passing a list of sorting extractors and a list of names. In this case, we have cluster and ironclast. Actually, this basically argument tells you whether when you merge the spike trains, you want the union of the 2 spike trains or the intersection of the 2 spike trains. And union here is actually the default, and then we'll make it verbose. And if we run it, we can see that the first, these cluster and ironclast are compared. And if you have more than one, all the pairwise comparison are made. And then we build a graph. And then by basically looking at the edges of the graph, we can see which units are in agreement with each other, also using multiple sorters. So this was really developed with more than 2 sorters in mind. And then we can actually plot some widgets. So here, basically, it shows us that in total, we had around 57 units, 49 plus 8, but only 8 were found by K is the number of sorters which agree upon n number of units. So only 8 units were found by both. And we can also split, we can also check this out. Yes. Okay. And we could also show this plot divided by sorter. So we can see that for cluster, 8 units are in agreement and 44 are only found by cluster, but also for ironclast, 8 units are in agreement and 5 are only found by ironclast. And these 5 might ring a bell because basically it's the number of units that we removed before for manual curation, right? So then when we have this object called MCMP, which by the way, it's a type MCMP, MCMP. Oh, I can't type today. This is a multi-sorting comparison object. It has some very handy functions that allow us to extract this ensemble sorting or agreement sorting. So we can just call this get agreement sorting and setting the minimum agreement count to 2. And this will retrieve a new sorting extractor object only with the units in agreement. And we see that now we have 8 units. 1, 2, 3, 4, 5, 6, 7, 8. Now, what we could also do is comparing the output of our manual curation to the output of this agreement sorting. And we can do that by assuming that our manual curation was perfect. So we can basically consider that as ground truth information and use this spike comparison compare sorter to ground truth function, passing the ground truth sorting extractor and this tested sorting extractor. And it's done. And we can plot the agreement matrix between these two. And we can see that basically almost all units that we manually curated are the ones that are found by this ensemble spike sorting, except for one. So this unit 10 was not found. So it's another unit that we might have removed. It might have been a noise that was found by both sorters, or it also might be a unit that we removed from the spike sorting output that was actually a good unit after all. And of course, we can, since this is a new sorting extractor object, we can export it to Phi and look at it with the nice Phi GUI as well. Okay, so now we've come to the very last part of this tutorial and the very important part, because as I mentioned before, or maybe I mentioned it this morning, but SpikeInterface supports over 20 plus file formats from acquisition systems, and also more than 15 output, like 15 sorted data file formats. And so we could actually use it, and you could actually use it to convert your data directly to NWB with like a few lines of code. And you can also pass some metadata along this process. So in this case, we want to pass the metadata saying that the device that we use, it's actually an OpenEFIS, it's called OpenEFIS, and it's an OpenEFIS acquisition board. And we can then just call the SpikeInterface NWB recording extractor. It has this static method called write recording, and we can just pass our cached recording file that we have already filtered and applied CMR on. We call it SpikeInterface tutorial.nwb, and we pass along this metadata. It's setting the time zone, and it's done. So now we have our, let's go back here. We actually have our NWB file over here. No, I don't want to open it. And on top of it, since we can save the Spike sorted data, in this case it's the iron class data, to the same file, right? And we can just call the Spike extractors NWB sorting extractor write sorting. So before it was run recording, now it's write sorting, passing the iron class output and the same file. And this will take a little bit more because basically it's also saving all the features and properties that we've used and we extracted. So it's saving the templates, the waveforms, and we're still in the process of extending these readers and writers to allow the users to select a subset of features that they want to save or discard, similar of properties, and so on. But now this is an NWB file, so you can open it with your HDF view, you can open it with the NWB widget, you can upload it to Dandy, and you can also reload it to NWB using the recording extractor and sorting extractor for NWB files. And that, of course, you can do with any NWB file that you have or that you download or that you create. Again, this is taking quite some time for the sorting extractor because it's reloading all the waveforms, all the templates, and everything. But after this is done, basically you're ready to go with further analysis and or adding new metadata to your recording or spike sorting again if you want, and so on. Okay, now it's loaded. We can see that so which one did we say? The recording cache. So it's a recording extractor again, and it works basically the same as everything else. It doesn't have channel 2 because we removed it. We can see sorting NWB, what gets shared, channel property names, name as up. Okay, you can see we have all the info. So basically everything that you do in the post-processing and the validation, it's saved as a property. So now we have saved all the information that we have computed so far. And this is a good way also to make your NWB file quite rich before uploading it to some, like to Dandy or look at it in NWB Explorer and so on. Okay, so this was the end of the tutorial. So I'm sorry I went 10 minutes over. I always do it and I always apologize. There's a question on the chat, and just you can write other questions or just speak up if you have other questions. So the question is, the consensus curations is like a very good idea. Do you have an idea of the percentage of units that survive this curation on average? How good is the match of consensus units with real units in ground truth dataset? So that was asked by Pierre. And Pierre, I'm just gonna point you to the SpikeInterface preprint on archive, because that's exactly what we analyze. And we show that basically spike sorters do not agree with each other at all. But on the other hand, if you do this consensus using a large number of spike sorters. In this case, we used the NeuroPixels data, both real and simulated, and we kind of proved that almost all the units that are not in consensus are on the ground truth dataset are false positive units. And we also showed that basically this consensus approach has very good agreement with manually curated data. So can you see this? So this basically, yeah, it's the same plot that I've shown before, but now with 6 sorters and the NeuroPixels dataset. And you can see that out of like more than 1,500 units that are found in total, only 33 are in agreement with all 6 sorters. So this, it was a bit scary when we started to get these results, but this is actually similar on simulated data. But on simulated data, we showed that most of the units, these red ones that are only found by one sorter, are false positive units. And then we also show that this consensus basically approach has a very large agreement over like 75 or 80% with the data manually curated by 2 experts. So we're not saying that this could be basically, it could be used for automatic curation as it is, but it could be used, for example, to flag units as being very good or okay, depending on how many spike sorters have agreed upon that unit. I hope that answers your question. Other questions? No? Okay, then I think we can actually, then we could close this session.